Irrational numbers are numbers that cannot be described as the ratio of two integers. Most numbers that we deal with in our day-to-day life can be described as the ratio of two integers, or one integer divided by another integer. Or another way of describing that is a fraction. And it's interesting to note that there are numbers for which this does not hold, and real numbers. So one example of this is the square root of 2. So I'm going to go slowly through a proof, just talk it out, about why the square root of 2 is irrational. Okay? So this is going to be a proof by contradiction. Proof by contradiction is we say, what if it was rational? We assume that it was, and then we see that it leads to a contradiction down the road. So I think the ideal way to learn this is to play this video over and over again and stop at the points that you have confusion, and if you do, then you can message me or look to another resource. But try to understand it a little bit at a time. Okay, so suppose the square root of 2 was rational. So we're supposing, on the contrary, that, what if it was rational? Well, let's see what happens. Then, the square root of 2 could be described as the ratio of two integers. Call them p and q. So, a rational number is defined as a number that can be described as the ratio of two integers, and we're just using the definition. Thus, the square root of 2 is equal to p over q, the fraction p over q, the ratio of p to q. And let's assume that this fraction is in simplest form. This assumption is key, but you might be wondering, wait, what gives us the right to assume it? Well, it's not very difficult to find the simplest form of a fraction. All we need to do is find all the factors of the numerator and the denominator and divide accordingly until we get the simplest one. So, even if it wasn't in simplest form originally, for any fraction, we can easily find the simplest form, so we might as well just assume that it's in simplest form. We can do it. By squaring both sides, we have 2 is equal to p squared over q squared. That's simple algebra of how we square both sides. This new equation, 2 is equal to p squared over q squared, shows that p squared is even, because if we multiply both sides by 2, we have p squared is equal to 2q squared. Now, p squared is even because 2 is a factor of it. 2q squared is going to be even, thus p squared is even. This shows that p, all by itself, not just p squared, but also p, is even. Because if a square of an integer is even, that means that the integer is going to be even. For instance, 2 squared is 4. 4 squared is 16. If you know that the square number is even, the integer that you're squaring has to be even also. When a number is even, we can express it as 2 times another integer. And in this case, we write p is equal to 2 times k. And I neglected to write that k is an integer, but k must be an integer. So this fact that p is even allows us to show that q squared is even as well. So since p squared is equal to q squared, that implies, and all we did is just divided both sides by 2 and replaced p with 2k. This implies that q squared is equal to 4k squared divided by 2 and is equal to 2k squared. So I encourage you to write this out and actually do the substitution to prove that I'm not just lying here. Since there's a q squared is equal to 2 times k squared, this proves that k squared is also even. And thus q is even for the same reason as p is even. Because if its square is even, that means that the integer itself is even. Since both p and q are even, the fraction p over q is not in simplest form. Because we can divide both the numerator and the denominator, both p and q, by 2 to get an even simpler form of the fraction. This contradicts our assumption. Because we showed that our assumption that square root of 2 was rational led to a contradiction, this shows that the square root of 2 is irrational. Now, it really is a remarkable thing that the square root of 2 is irrational. For one, it means that if you have something of the length of square root of 2, there does not exist a ruler that could exactly measure it at the line of the ruler. This is called mensurability, and I think I'll discuss this more in a later example. Suffice it to say that irrational numbers are numbers that aren't ratios of two integers, and they exist. We showed at least one example. Other examples include pi, square root of any non-perfect square, and a lot of other mathematical numbers that are pretty important. But this is just a first taste.